Next, let's move on to a very fundamental topic, which is sorting. And we're going to start with the insertion sort algorithm. Sorting is used all the time, and there's a ton of different sorting algorithms, all with their own trade-offs. It's usually applied to arrays like this one, but you can also apply it to other data structures, including linked lists and others. So in this case, we have an array of 5 values, and clearly they're not in order. They're not in ascending order, which would be in increasing order, like 1, 2, 3, but they're also not in decreasing order, which in this case would be 6, 4, 3, etc. Suppose we want to sort them such that they are in ascending order. So our target array would look something like this, 1, 2, 3, 4, 6. We can achieve this with the insertion sort algorithm. Let's see how we can do it. Well, the main idea is to break the problem into subproblems again. So if we want to sort the entire array, the first thing would be to have the first portion of the array, meaning just the first element, have this sorted. Well, one value, like 2, is sorted by default. I mean, how could this be not sorted if it's just one value? So we consider any array of one value to be sorted. The next thing to do, the next subproblem, would be to sort the first 2 values, make sure these are sorted, and then have the first 3 values sorted, and then have the first 4 values sorted, and keep doing that until we have the entire array sorted. So thinking of it this way in terms of subproblems makes the algorithm a lot more simple. Now, since we are doing it with subproblems, technically if we wanted to, we actually could solve this using recursion, which is a technique we just learned, but it's not really useful in this case, so I won't do it. We can do this without recursion, aka we can do this iteratively. We can have an iterative solution, which is using loops. Now the idea is we're going to loop through the array, but we're going to start at the second element because we know that this subarray is already sorted. So starting here and assuming that every value before this position, meaning this subarray, is already in sorted order, our goal now is to have this array be sorted. So our goal really is to figure out where to put this value. We already know all of these are sorted. Where should we put this one in terms of this array? In this case, we don't have a lot of choices. The logical thing to do is compare this value to the only other value in our array. Is this larger? If this is larger, then it should stay where it is. If it's smaller, it should be swapped with the value over here. Since this is larger, it can stay here. Now there's the other edge case where what if both of these are equal? If that's the case, this value can also stay here because it doesn't matter whether this goes here or here if they are both equal because it'll be sorted either way. This is for ascending order, but it would work the same way with descending order as well. So now that we know where this value should go, it should stay where it is, we can now move to the next value. So by the time we get here, we know that this subarray is already sorted. So at this point, we're going to do a similar comparison. We're going to compare this to its left neighbor. Is 4 greater than 3? Yes, it is. So it's going to stay exactly where it is. And at this point, we didn't even compare 4 to 2, but we don't need to. Do you know the reason why? Well, we already know these were in sorted order. So if 4 is greater than 3, of course it's going to be greater than every value to the left of 3 because these are sorted. Every value to the left of 3 is going to be less than or equal to 3. And now every value to the left of 4 is going to be less than or equal to 4. So at this point, we know that these values are in sorted order. We can shift our pointer to the right by 1 over here, and now things are going to get a little bit interesting. So now we have this sorted portion, and we have to figure out where the 1 should go. Should it go at the end of these 3 values? Should it go in between these 2 values? Should it go in between these 2 values? Or should it go over here? Well, let's see what the algorithm does. This is why it's called insertion sort, because we're taking one value and inserting it into a sorted array. So let's see what the algorithm does in this case. First, we're going to compare 1 to 4. Is 1 greater than or equal to 4? It's not. So now we finally execute the other case. And by the way, the pseudocode for this would look something like this. Remember our pointer, which is I, in this case, started at index 1, and we're going to keep going until we've reached, the end of the list. So that's pretty straightforward. And now we're going to get to the interesting part where we compare this to the neighbor. So we have a second pointer for the neighbor. We call that j. This is at I, or you could also call this j plus 1. That's what we're going to be doing. And then you compare these. And now the value at j plus 1 is less than the value at j. That's this part of the code. This part is basically to make sure that we don't go out of bounds. And you'll see what I mean in just a second. But now that this comparison holds, we're going to perform the swap. This is where we take this value and move it over here and take this value and move it over there. So the first thing we would do actually is take the value that was originally at j plus 1, which is 1, and put it in a temporary variable, because what we're going to do is now at this index j plus 1, we're going to move the value that was here. So we're going to put a 4 over here. And then over here, now that we've lost the 1, we have to use our temporary variable. So we're going to put a 1 over here from our temporary variable. And originally our j pointer was over here. We're going to decrement it by 1, which means we're going to shift it to the left by 1 over here. And the reason this is a while loop and not just an if statement is because now we're going to continue this whole process. We originally had the 1 over here, and we know it should be shifted to the left because it's definitely less than 4, but we don't know that we're done. We don't know that this is the final spot that this 1 is going to be. We have to continue comparing to the left neighbors. So now we're going to execute the condition again. First, we're going to make sure that j is not out of bounds yet, because as we keep shifting it, we know at some point it's going to be all the way over here. It could be out of bounds, but right now it's not out of bounds. We know that because it is greater than or equal to 0. And now we're going to compare the value at j plus 1 to j. J plus 1 is less than the value at j. 1 is less than 3. So now we're going to do the exact same thing. We're going to perform the exact same swap. So now we have our 3 over here and our 1 over here, but we're not done yet. We're going to decrement our j one more time. So now j is going to be over here. It's still in bounds. And the value at j plus 1 is again less than the value at j. So now we're going to do another swap. So the 2 is over here and the 1 is going to be over here. And now j is going to be shifted to the left by 1 again. Now it's out of bounds. So now there's no point in even doing a comparison. That's why we're checking that it's in bounds before we do this. We don't want an index out of bounds error. So since it's not in bounds, we can stop doing this loop. And we know now that our I pointer, by the way, was over here. So now at this point, our I pointer is going to be shifted over here because we're going to execute the next part of the for loop, the outer loop that's over here. And we know because of that, this portion of the array, these first 4 values are now in sorted order, and they look sorted as well. 1, 2, 3, 4. So now that our I pointer is over here, our j pointer is going to be initially over here. J is in bounds. So now let's compare the two values. Is 6 less than 4? It's not. So we know that this is greater than 4. Therefore, it's going to be greater than all of these as well. So that means that this is already in sorted order. Our outer for loop is now going to stop because there's no more elements over here, left for us to traverse. Now we've been talking about sorting integers so far, but of course this could be applied to characters. If we had something like B, C, A, as long as we have a way to compare characters, so in this case, let's say we're sorting based on just alphabetical order, we can basically sort any set of values as long as we have a way of comparing two values together. So in this case, we could sort these to be something like ABC. Of course, we could also sort strings themselves the same way a dictionary sorts words. So a word like apple would go before a word like banana. With sorting, there's also this notion of stable versus unstable sorting. Let's say we had this array of values 7, 3, 7. Any sorting algorithm is going to take these values and put them in sorted order, which would be 3, 7, 7. Any sorting algorithm could do that, but the difference between a stable sorting algorithm and an unstable sorting algorithm is this. This is what a stable sorting algorithm would do. It would put the numbers something like this. The thing to notice here is that for 7, it appears twice in the array. So this first 7 could have gone here, and then the second 7 would have gone here. Or they could have been in reverse, right? This 7 could have gone first, and then this 7 would have gone second. Both of those are valid sorting order, but a stable sorting algorithm will preserve the original order when there's a tie. We know that there's 2 7s. And for some reason, if we wanted the original relative order of these 2 7s to be preserved, meaning this one showed up first before this one, so it should go first in sorted order. That's called stable sorting. Unstable sorting might achieve this, but there's no guarantee. It's not necessary that that will be preserved, so it could have flipped them for some reason. We'll touch on this again as we continue. But my question for you, based on this, do you think the insertion sort algorithm is stable or is it unstable? Well, let's quickly go through how it would execute on this. First, our pointer would be over here. We would compare the 3 and the 7. They're out of order, so we would swap them. So then our first 2 values would look like this. So that's good so far. And then our third pointer would be over here, right? And this would be a 3 and this would be a 7. And we would say, this 7, is it less than the 7 on the left of it, right? That's where this would execute. This 7 is not less than that, so it's going to stay exactly where it is. So therefore, we would achieve this output where the relative order in case of a tie would be preserved. These two would stay in the order they were in originally. So based on this implementation, this is a stable sorting algorithm. It's preferred to keep an algorithm stable if you can. We could code this in such a way where it's not stable, but that would have no benefit for us. So we're going to keep it as stable. So now finally, let's talk about the time complexity, which is interesting for insertion sort actually. And the best way to actually understand it is to look at a couple examples. Let's say we were running insertion sort on a list that's already sorted. What would the algorithm do? Well, we would have a pointer over here. We would want to, of course, iterate through the array, but then we would do a comparison. From here, we would compare it to the left neighbor. They're already in sorted order, so we don't have to do anything. We can shift our pointer over here. We compare these 2 values. They're already sorted. We don't have to do anything. We shift the pointer again. Then we compare these 2 values. They're already sorted. We don't do anything. We shift the pointer. We're out of bounds. That means we're done. So as you can see, when we have an array that's already sorted, we run insertion sort, and the execution is just iterating through the list, which is big O of n time complexity. Of course, we have nested loops here, but just because we have a loop here doesn't mean it's necessarily going to execute. I just showed you an example where this inner loop is never going to execute. So in this case, the best case time complexity is big O of n. Now, technically, big O means worst case, so I'm kind of misusing it here, but it's kind of common for people to talk about it this way. But in this case, I'm saying the best case time complexity, which would occur when the input is already sorted, is going to be linear time complexity. Let's look at the other case, where is the worst case time complexity, which would actually occur on the opposite example, where the input is in reverse order and we want to sort it in ascending order. So in this case, again, we would loop through the array. We would start here. We would compare the 2 neighboring values. We would see that they're out of order, so then we would have to swap them. We would put the 3 over here and the 4 over here. Then we would shift our pointer over here, and then we would compare these 2 values, and then we would see they're out of order. We'd have to swap them again. We would have to put the 2 over here and the 4 over here. And at this point, we're still not done yet. This 2 is going to be compared to its left neighbor now, and they're again out of order, so we would have to put the 3 over here and the 2 over here. So you can see it's definitely getting messy. But ultimately what we would find is we would have to take this 3, shift it over here. Then we would get our pointer over here. This 2, we would have to shift it here, and then we would have to shift it here. Then when we get to this 1, we would have to shift it to the left, then shift it to the left again, and then shift it to the left again. So for every single value that we iterate through, the inner while loop would have to execute the maximum number of times until that value is shifted all the way to the left. When we get to the 2, we'd have to shift it all the way to the left. When we get to the 1, we'd have to shift it all the way to the left. Now for an input size of 4 in this case, n squared time complexity would look like 4 squared, because the length is 4, which would be something like 4 plus 4, right? Added together, how many times? Well, 4 times. That's just the math formula here. But this isn't that. What we were doing right now was actually a bit different. What we actually have is something like 1 and then plus 2 and then plus 3 and then plus 4, because for this value we might have to, consider it to be in these 2 positions. For this value it could be in these 3 positions. For this value it could be in these 4 positions, which correlates to that 4. And I just talked about the 2 and 3 case. And we might not have a 1 case because remember we're skipping the first index, but again, this is just an approximation. And that's enough for us when we're doing big O time complexity. Now, what most people do when they have nested loops, they automatically assume that the time complexity is big O of n squared. And usually it's the correct assumption, but I bet most people don't know why that's the case. And I'm going to explain it to you briefly right now. This equation is bounded by n squared. It's pretty obvious when you look at it like this because every term here is greater than or equal to every term here. But I'm going to show it to you in terms of big O time complexity, where remember, we know that constants don't matter when we're multiplying by a variable, right? So some constant c times n squared doesn't matter regardless of what the constant is. I'm going to use this idea to prove it to you that this is bounded by n squared, and I'm not even going to use a math proof. Now, maybe I'm not smart enough to show you the math proof of why this is true, but I'm smart enough to draw a picture, and that turns out to be enough. We know that n squared, where n is 4, would look something like this in terms of geometry, right? 4 times 4, right? This is us having to iterate through an array of size 4 times. We have to do that. We have to iterate through it once, twice, 3 times, 4 times. But we also have the case where we iterate through just, let's say, the first value of the array, and then the first 2 values of the array, and then the first 3 values of the array, and then the first 4 values of the array. So maybe now it's becoming a little more obvious why this is bounded by this. And not only that, this is actually pretty much exactly half the size of n squared. And we even talked about how the first term in this case doesn't actually apply. So maybe this isn't even there, but it's still, you can see, approximately half the size of n squared. We didn't even use a math proof to figure this out. This is obvious enough from looking at a picture. So if this is half the size of n squared, we can write it as n squared divided by 2, or in other words, 1/2 times n squared. And this is just a constant, remember, and we don't care about constants. So we can say this, or in other words, iterating through an array like this would be the same as big O of n squared time complexity. That's the worst case time complexity of insertion sort. So that was a lot to cover, but to finally wrap up our first sorting algorithm, insertion sort, which is a stable sorting algorithm, has a worst case runtime of n squared, but it's also worth mentioning that the best case runtime is big O of n. That's not always true for other sorting algorithms, but it does turn out that there's better sorting algorithms than n squared worst time complexity.